Alright, welcome to lesson 4. Here we're going to take a look at some situations in which you can apply optimization principles to economics. So let's go ahead and get started by taking a look at this problem. And what we'll see is that the relationship, the economic principle that we're looking at is one that's pretty simple and that you are already familiar with. So go ahead and read through this problem, complete parts A through E, and then we'll talk briefly about it and see what we have discovered. Okay, so as I'm sure you were able to figure out, to determine the profit, or the amount of money which you end up with, you're going to need to subtract the cost of producing X number of items from the revenue that you make from selling X number of items. So the profit, P of X, is equal to R of X minus C of X. Pretty simple relationship that you're already familiar with. Is P of X differentiable, and why? Now, notice that R of X and C of X were both differentiable functions, which means you could take the derivative of both R of X and C of X. So if you wanted to take the derivative of P of X, you could do so because the functions that it is made up of are also differentiable functions. So P of X is differentiable because R of X and C of X are differentiable. And of course, when you take the derivative, all you need to do by the difference rule, taking the derivative of both sides of this function, you take the derivative of R of X, R prime of X, and the derivative of C of X, C prime of X. So even though we don't know exactly what these functions are, we know that they're differentiable, and so the derivative of the profit is going to be the derivative of the revenue minus the derivative of the cost. And we'll talk a little bit more about what this relationship means and exactly what it means to take the derivative of a revenue, cost, or profit function. Alright, to find the maximum profit now, what must be true? So you're thinking about the profit function, and you want to find a maximum value for your profit function. Well, just thinking about our optimization strategies, if we want to find an absolute maximum for a function, we want to first take our function, we want to find the derivative of it, and find any critical points, because we know that a function will reach an absolute maximum either at a critical point or an endpoint. So if I have my function P of X and I take the derivative of it, which I have done here, to find the critical points, I'm going to set my derivative equal to 0. Now, P prime of X is the revenue, the derivative of the revenue, minus the derivative of the cost. And so this will occur when R prime minus C prime is equal to 0. Looking at this relationship, what you notice is that the derivative of the revenue minus the derivative of the cost must be equal to 0, which means these two things have to be the same. And by adding C prime of X to both sides, you can see that relationship. R prime of X will equal C prime. And this is an interesting relationship. What this is saying is that in order for a maximum profit to occur at a given value X, in other words, for your derivative of profit to be equal to 0, that will be the case when the derivative of the revenue is equal to the derivative of the cost. And thinking a little more deeply about what it means to have the derivative of a revenue and a derivative of a cost function, remember that the derivative is the instantaneous rate of change at some value X. Now X here represents the number of items that you've sold or produced, and the derivative is then saying that at that instant, at that level of production X, this is the amount by which your revenue is changing, or the amount by which your cost is changing. So it gives you a snapshot into, at that particular value X, when you're producing or selling that many items, how much is your revenue or your cost changing? Maybe it's decreasing, maybe it's increasing, so you can get an idea of whether or not selling more or less of your products is going to either increase or decrease your revenue or cost. And then this relationship is saying when the instantaneous rate of change of the revenue and the instantaneous rate of change of the cost are equal, that is a possible value, at a possible production level, X, at which you could have a maximum profit. All right, and we're going to dig deeper into this in just a second. But that is an interesting relationship to see, and that's one that we're going to exploit. So in our study of optimization within economics, we're going to look at three functions and deal with those primarily, those functions and their derivatives. So the functions are the revenue, the cost, and the profit. Of course, the profit is the difference between revenue and cost. And our independent variable x refers to the number of items either that we're selling or producing. Now, we discussed the derivative of these functions, and looking at the derivatives of these functions is what's called marginal analysis. Now, before we get into the definition here, I want to recall what our brief discussion in the previous question about how to interpret the derivative of the, for example, revenue function or the profit function. So let's just think about the revenue function for a second. If you take the derivative of it, you're taking the change in revenue with respect to x, meaning that at that instant, how is the revenue changing with respect to changes in x? And so when you're looking at this particular value, so let's say you have r prime of 100, so you're selling 100 items. The derivative at that point is telling you how much your revenue is changing at that instant when you're selling 100 items. And that gives you an idea of what would happen to your revenue if you were to sell 101 items or 102 items. So let's just take a quick example. Let's say that you knew r prime of 100 was equal to 15. And this is going to be, of course, dollars, right? Revenue. So $15 per item. Now, at this exact instant, this tells you that when you're selling 100 items, your revenue is in the midst of increasing. And so your hypothesis then would be if you were to sell 101 items, then your revenue would increase because the rate at which the revenue is changing at this instant is positive. And the same is true for cost and profit. So let's make sure we have this idea captured. Marginal, and here I put a blank in so that you could say it's either marginal revenue, marginal cost, or marginal profit, is the instantaneous rate at which the revenue, cost, or profit is changing when X items are sold or produced. It gives you an intuition as to how a small change in the number of items will affect either the revenue, the cost, or the profit. And marginal analysis is something that is used very often because it gives you some important information, right? You'd really like to know at particular production levels, depending how many items X you're making / selling, what that's going to do to your revenue, your cost, or your profit. And that way you can make decisions on whether you should try to increase production, decrease production, and how that will affect your overall take home or your profit. And so with this, we can combine these ideas, and looking back at what we discovered in that problem that we did at the beginning, we noticed that there was a relationship between the marginal revenue and the marginal cost. We saw that when we were trying to find a maximum value for the profit, before doing that, we had to find any critical points because those are the candidates for potential places where the profit is maximized. And we found that those critical points will occur when the revenue, the marginal revenue, is equal to the marginal cost. In other words, the instantaneous rate of change at which the revenue is changing is equal to the instantaneous rate of change at which the cost is changing. That's very interesting, and it's something that makes our life a lot easier. So let's actually prove that this is the case. So there are two theorems that we're going to take a look at and prove. The first is a theorem for maximum profit. So maximum profit, if any, and this is an important component here, if any, doesn't necessarily have to occur. But maximum profit, if there is any, occurs at a production level for which marginal revenue equals marginal cost. And when you hear this word production level, what you're thinking about is the X value, right? How many items are you producing slash selling? So maximum profit, if any, occurs at a production level, or number of items produced or sold, for which the marginal revenue equals the marginal cost. In other words, the derivative of the revenue is equal to the derivative of the cost. And so to prove this, there are a couple things that we need to do. First, we need to assume that our revenue and our cost functions are differentiable. And this is, of course, important. We need to assume that these are differentiable because our way of finding a maximum, absolute maximum, requires us to take the derivative of a function, and in this case, the derivative of profit. And the profit function is made up of the revenue and the cost functions. Now, we know that if we're finding a maximum profit, we're maximizing the profit function, and where are the places that a function could have a maximum? Well, it can have a maximum either at its endpoints or its critical points. Now here it's pretty clear there are no endpoints. You could theoretically produce as many products as you want. So the only possible points or levels of production at which a maximum could occur are where P prime of x is equal to 0. In other words, a critical point. So if the profit has a maximum value, remember it doesn't necessarily have to, but if it does, it will occur at a production level, meaning a value of x, for which P prime of x is equal to 0. Now, simply by setting the derivative P prime of x equal to 0, we can then imply that since P prime is R prime minus C prime, that means R prime minus C prime must equal 0, and therefore R prime equals C prime, or the marginal revenue must equal the marginal cost. So we have the derivative of profit, P prime of x is equal to R prime of x minus C prime of x. In other words, the marginal profit is equal to the marginal revenue minus the marginal cost. So when we set this equal to 0, this of course means that R prime minus C prime must equal 0. And of course, if R prime minus C prime is equal to 0, this means that R prime must equal C prime at that particular x value. So we've proven that if there is a maximum profit, notice there doesn't have to be, but any place where it would have one is a place where the marginal revenue equals the marginal cost, or that at production level, the marginal revenue equals the marginal cost. So when looking for a maximum profit, we can use this to our advantage. We can simply look for where the marginal revenue is equal to the marginal cost, whatever that x value or production level is, and those will be the only possible places that a maximum profit could occur. It doesn't have to, but it could occur. Let's take a look briefly at an illustration. It's actually on page 228 of your book here, and it's a nice graph of a revenue and a cost function, and will help us visualize why this theorem is true. Alright, so taking a look at this graph, we notice we have a cost function graphed in blue, a revenue function graphed in darkish pink, and we'll notice a couple of things as well. The x-axis, of course, represents items produced, it's production level, and the y-axis represents dollars. So there are a couple of things that I think are really easy and intuitive. The first is that whenever revenue equals cost, there you're going to break even, right? And that should make sense. We discussed that last year. And now we want to take a look at the theorem that we just proved, which is wherever there's a maximum profit, it will have to be the case that the revenue, the derivative of the revenue, is equal to the derivative of the cost. But it's not necessary that at that point it is a maximum profit. So let's take a look at the first situation where this occurs. Here we see that the tangent line for the cost, which tells you the slope of that at that instant, and the tangent line for the revenue are the same here. But notice that just because they are equal does not mean it's a maximum profit. In fact, in this case, revenue is less than cost, which means you're actually losing money. And this turns out to be a maximum loss or a minimum profit, right? That's where this if any comes in. Just because we found a critical point doesn't mean it has to be a max. It could be a min, okay? And that's important to remember. Here we see the situation arise again. we see that the derivative of the revenue is equal to the derivative of the cost. In other words, marginal revenue is equal to marginal cost. And I want to stop here for a second to remind us of our interpretation for marginal revenue. What marginal revenue tells you is that this particular production level, this is the instantaneous rate at which the revenue is changing for this particular production level. So here you can see that it's increasing ever so slightly. So that would lead you to believe, and correctly so, that if you were to increase your production just a little bit, you would also increase your revenue just a little bit. However, notice that the same is true for the cost. So if you were to increase your production just a little bit, it seems that your cost would also increase a little bit. So it's not necessarily the case that increasing your revenue will lead to increasing your profit, because your cost will also increase. Now, at this particular point where they are equal, where the marginal revenue and the marginal cost are the same, here we have a maximum profit, and that is because the revenue is now greater than the cost, and so here we'll have a maximum for the profit. And you can kind of see that if you were to move anywhere to the left or to the right, that discrepancy between revenue and cost would diminish. In other words, your profit wouldn't be quite as large. So this is a very helpful graphical representation to represent the theorem that we just proved, and we'll make use of it in just a second. But now let's go ahead and take a look at another theorem which I think is also quite interesting. So this next theorem talks about average cost and trying to minimize average cost, and that should make sense. If you're running a business, you'd like to minimize the cost to produce each item on average. So the production level, if any, at which average cost is smallest is the level at which the average cost equals the marginal cost. So let's remember that average cost, so if we want to know what the average cost is, we'll take the cost for a certain production level. So say, X were 100, could be 200 or whatever. That would be the total cost to produce X number of items. Well, that means the average cost will be the total cost divided by the number of items. So average cost is C of X over X. And marginal cost, of course, remember that is the derivative, so that is just C prime. Okay. Now, we want to make average cost smallest. We want to minimize the average cost. And remember, a minimum or a maximum will occur at critical points for this particular function. So this function will need to be minimized, and therefore we want to take the derivative of this function and set it equal to 0. So average cost will be smallest when the derivative of this equals 0. Okay, so that's writing out this statement. Remember I said if. It doesn't have to be the case that there is, in fact, a smallest value at each of these critical points. But if there is a minimum average cost, it will occur at a critical point, and so we'd like to find all of those critical points. In other words, where the derivative of our average cost is equal to 0. If I want to take the derivative of this, this is a function of x divided by a function of x. So I need to use the quotient rule. Now the quotient rule applied here gives me the following. So of course I have x squared as my denominator, then I have x times the derivative of c minus the derivative of x, which is 1 times c of x, and that has to equal 0. Now if I multiply by x squared on both sides, and that will of course give me 0 on the right and just my numerator here, and again that should make sense because when I have a rational expression set equal to 0, all that I'm looking for is where the numerator is equal to 0. So multiplying by x squared on both sides will give me, and so this says that you will need x times c prime of x, or the number of products that you're making times the marginal cost minus the cost to be equal to 0. Remember, we were trying to conclude that this will occur at a level where the average cost equals the marginal cost. Now marginal cost is this here, so we'd like to isolate this. So if I add my cost function to both sides and then divide by x on both sides, I'll have exactly that. And so what I've done is I've shown that if the average cost has a minimum value, that minimum value will occur when marginal cost is equal to average cost. And this can be helpful as well. If I want to know where my average cost of producing an item is smallest, I need only find the places where the marginal cost is equal to the average cost, and then test any of those critical points to see if it is in fact a minimum value for the average cost. Important to stress that both of these theorems say that if there is a, in this case, maximum profit, or if there is a minimum average cost, it doesn't guarantee that any place where this is occurring or any place where marginal revenue equals marginal cost, it's not the case that at each of those points there will be a maximum profit, or at each of these points there will be a minimum average cost. But if there is, it will occur where either of these situations arises. So let's go ahead and apply these to a couple of scenarios. Okay, so suppose that your revenue function is 9x and your cost function is x cubed minus 6x squared plus 15x, where x represents thousands of units. Is there a maximum profit, and if so, what is it? So go ahead and construct a plan on your own first. What are you going to do? What theorem could you apply? And work through this on your own, and then we'll take a look briefly at the solution. Alright, so pretty simple situation here. We have a revenue function and a cost function, and our theorem says that if there's going to be a maximum profit, it will occur in a place where the marginal revenue equals marginal cost. So I want to find the derivative of each of these functions, set them equal to each other, see what x values satisfy that equation, and then test each of them to see if either is a, or any of them is a maximum profit. So that's my plan. If that helped you out, go ahead and pause again and work through this on your own. If not, let's go ahead and take a look. So taking the derivative, finding the marginal revenue and the marginal cost, I then want to set the marginal revenue equal to the marginal cost. I notice, of course, in doing that I end up with a quadratic equation, so I'd like to clear one side out and make it equal to 0, and that will allow me to either factor or use the quadratic formula. Okay, so I go ahead and do that by subtracting 9 from both sides. I try factoring, so I factored out a 3, and then I am left with this quadratic here, and I can't factor this. Two things that multiply together to be 2. The only options that would make this easy are 1 and 2, and no scenario will lead us to -4 when we add those together. So I'm going to go ahead and use the quadratic formula, set this equal to 0, use the quadratic formula to solve for x. So solving, I get two x values. I'm actually going to call them x1 and x2 to help me, x sub 1 and x sub 2, to help me delineate between the two of them, because they're two different x values, of course. And these represent the production levels at which r prime will equal c prime. And so notice here that the x values are in thousands of units, so this would of course be a little more than half a thousand, so about 586 exactly. And this would be 3,414 units. So now notice I have two values, and not each one has to be a maximum profit. So what we need to do now is test each of these x values with our profit function to see which one will give us a maximum profit. So testing both out in my profit function, of course remember the profit function is just the revenue function minus the cost function. So applying both of these x values, I see that for the first x value I actually get a negative value, which means my profit is negative. I'm losing money. At 3.414, or a production level of about 3,414 items, I'm actually going to have a positive profit, and so this will be my maximum profit. This one will not be. So I will have a maximum profit when I'm producing 3,000, or approximately 3,414 units. So that would be your solution. Remember, we always have to interpret our solution in real-world situations. So I'm not going to write this down, but how you would write down your answer, and you should do this now, is that there will be a maximum profit at approximately 3,414 units produced, or when producing approximately 3,414 units. Now let's go ahead and take a look at a situation where we're looking to minimize the average cost of a unit produced, and that's another way that you can help your company be successful. Obviously maximizing profit is something you're looking to do, but also looking to minimize the average cost per item is something that would definitely be beneficial to your success. So here, suppose that your cost function is given, and it's actually the same cost function as before, and where X represents thousands of units. Is there a production level that minimizes average cost? If so, what is it? So go through and determine a plan of action, and go ahead and try and carry it out on your own, and then we'll take a look together. Okay, so minimizing average cost means I want to look for places, production levels, X values, where the marginal cost, the derivative of the cost, is equal to the average cost. And those are going to be the places where I could have an absolute minimum. Notice I don't have to have an absolute minimum there, but I could have an absolute minimum. So we'll want to find marginal cost, we'll want to set it equal to average cost, and solving for X for that particular production level, and then test whether that particular production level is in fact an absolute minimum or an absolute maximum. Alright, so I found my marginal cost here in blue, my average cost function here in green. Now I'm going to set them equal to each other. I want you to go ahead and do that on your own, set them equal to each other and solve. There are a couple different ways you can do it, and I'll discuss those in just a second. Alright, so you can go ahead and set these equal to each other straight off the bat, and if you do so, your first move will then be to multiply it by an X on both sides so that you don't have a rational expression on one side. But before doing that, you could also notice that X will divide in evenly to all of these, so you can just cancel an X in each of these terms, and you'll get X squared minus 6X plus 15, and then you can set them equal to each other. Either way works just fine. I'm going to go with the first way because I think it creates a little less work. So dividing an X into each of these terms gives me X squared minus 6X plus 15, and now I can go ahead and set them equal to each other and solve. So you can notice in my first step here, it's a lot less to deal with if I divide the X in first in my average cost function. If not, then I'll have cubics on each side, and I'll have to do a little more factoring on the back end of it. But at this point, I just have a quadratic equation, so my goal is to get one side equal to 0 and solve either by factoring or using the quadratic formula. So in doing so, I actually am able to factor this quite nicely, and that allows me to solve for X. X is either equal to 0 or X equal to 3. Now you might be tempted to say, okay, I have two X values, let's name these X1 and X2 and let's test them out. But X equals 0 means you're producing no products, and pretty sure that doesn't work for a business. So remember, in our theory, our theorem, we stated that X has to be greater than 0. So we're going to throw this critical point out. This does not matter for us. And we're going to test X equal 3 to see if it's an absolute minimum in this case. Remember, we're trying to minimize the average cost. So how can we test if it's an absolute minimum? Well, we have only one critical point here. So we have the option, we can use the first derivative test or the second derivative test, and I'll let you decide there and make your decision, and then we'll take a look together. Alright, so if you use the first derivative test or the second derivative test, the trickiest part is recognizing what you're using that test on. We are trying to minimize average cost, so we're looking for a minimum value of the average cost function. So if you're using the first derivative test, you are using the first derivative on this function, take the first derivative of it, and then use your critical point of 3 to test. If you want to use the second derivative, you'll take the first derivative and the second derivative of this average cost function, and then you'll evaluate this critical point based on the second derivative test. So either way, we've got to take the first derivative of this function. Again, that's why it was so helpful to divide in the X beforehand. It doesn't make it impossible if you don't, but it makes it a lot easier if you do. So we'll take the derivative of the average cost. Okay, so notice that once you've found the derivative of the average cost function, you can think to yourself, do I want to make a sign chart for this derivative? You know, noticing that, of course, the X value of 3 makes this equal to 0, and then on either side of it, you know, what are the signs going to be, and you can do that. But also notice that taking the second derivative here is actually going to be pretty easy, and taking the second derivative will give you a value of 2. Let's actually do that now. Notice here I've just taken the derivative of both sides of this function. So instead of the first derivative, I now have the second derivative of the average cost, and that is equal to 2. So remember what the second derivative test tells us. At a critical point, and our critical point is x equals 3, if the second derivative is greater than 0, meaning that I am concave up, that I will have an absolute minimum, since I have only one critical point, and if it was less than 0, it would be concave down, and that would be an absolute maximum. So since the second derivative is greater than 0, this critical point here is an absolute minimum, which means I've found an absolute minimum for the average cost. And of course, you want to write your answer down in terms of what the question is asking. You want to interpret it in this situation. So while I won't write it down, you should, so that you have a model to look back at. You want to answer the question, is there a production level that minimizes average cost? And if so, what is it? So you want to say that producing 3,000 units will minimize the average cost. And of course, you could write that a little differently if you wanted to. All right, at this point, go ahead and work through homework 5.04, and I will see you guys on Monday.